Hello guys, welcome back to Z Physics. Today we're going to be talking about the magnetic field around a current carrying wire. This was actually one of the most interesting experiments in the 19th century, which first probed the relationship between electricity and magnetism, two seemingly unrelated phenomena, which, as it turns out, would soon be unified into a single theory known as electromagnetism. What was first noticed was that magnets started behaving pretty strangely around the wire. In fact, you could essentially plot a magnetic field line simply by having a current carrying wire. We have this wire over here moving along with current I moving in this direction. If we were to probe the magnetic field around it with some magnets and we do a plot, we'll soon discover that the magnetic field around the current carrying wire consists of concentric circles. Really interesting, and those concentric circles are perpendicular to the plane at which the current is moving. One of the best ways to visualize this is with the following notation. Let's have a look at this notation first off. Now, let's think in 3D at the moment, just like in the cinema. Oh wait, no, that's looking at 3D, but let's think in 3D right now. Imagine that this over here is the back of an arrow. So it's the back of an arrow that's been shot and it's going into the screen. This is the convention for the direction into the screen or into the page on a test paper or into the board on a whiteboard in college, etc. And this over here is the tip of a arrow which is coming towards you. So in this case, this would indicate the direction out of the screen or out of the page or out of the whiteboard, etc. If we have a current carrying wire with which the current is going into the screen, we can see that the direction of the magnetic field will be clockwise. So this is a very useful fact to remember, that the magnetic field is clockwise when the arrow is going, when the current is going into the screen. If it's going out of the screen, we can see that the magnetic field lines are going to be anti-clockwise, like so. We can summarize this rule by essentially the right hand grip rule, which is an alternative way of trying to remember the same phenomena. You can see my little drawing over here of a thumbs up, which just reminds me, if you haven't liked this video, I think this over here is a good indicator to hit the like button. Now, looking at the current carrying wire, we can see that the current is going upwards. What we can always imagine to do if we have the direction of a current, imagine gripping a wire and align the thumb with the direction of the conventional current. Some exam questions may try and trick you by giving you the electron flow direction, but the current will be the opposite direction if that's the case. In either case, the direction of the conventional current in this case is upwards. So if we're to align our thumb with the direction of conventional current, we can see that the curl of the fingers will coincide with the direction of the magnetic field lines. And we can use this as another way of remembering the rule for drawing magnetic field lines around a current carrying wire. One more field I would like to have a look at in this online lesson is the magnetic field around a solenoid. Now, a solenoid is just a fancy word for a loop of wire. and often there are multiple loops of wire. So we have a wire over here, and we can see that we've looped this quite a few times. Normally there is a base and a core to the solenoid, but in this case it's just a wire that has been looped. We can use the right-hand grip rule to actually determine the direction of the magnetic field and plot a field around it, which I've done like so, given the current is going in the direction as stated. What we're going to find out if we were to do that is that the field inside of the solenoid is actually uniform. So this is really important. It is one of the ways to produce a uniform magnetic field. It's not quite uniform around the edges. Well, it's not uniform around the edges, as you can see, and the solenoid is going to act as if it had a north pole and a south pole. This is one way of essentially making an electromagnet, simply by looping a wire and then running a current through it. This will simulate the field around a bar magnet really effectively, and can be used for many purposes in research and in engineering as well. Okay guys, well, let's finish off by testing our understanding. We have a little question over here. We have a current carrying wire and the direction of the current is shown. What I want you to do is to state the direction of the magnetic field at the following points, 1 and 2. So please go ahead and pause this video and have a think. So the correct answer is that at point 1, the magnetic field is pointing out of the screen or out of the page if this was a test paper or if you're working on paper. And at point 2, the direction of the field is into the screen or the page. The way we get those two correct answers is once again using the right hand grip rule. It's really important, by the way, to use the right hand, because otherwise if you use the left you're going to get some opposite answers. Imagine that you grip this wire and you align the thumb with the direction of the current, which in this case is upwards. We can clearly see that the circular pattern around the wire will be pointing in the direction of the curve of the fingers. So this means that around this wire there's going to be some concentric circles which are going to be pointing in the same direction in which the fingers curl. Now we have to imagine this circle is in 3D, so at point 1 the magnetic field will actually be pointing out of the screen, and at point 2 the magnetic field will be pointing into the screen. Okay folks, well, hopefully this makes sense, and thank you very much for watching, and I'm going to see you guys in the next video.